Alright, let's look at lesson 1.4. This is the last lesson of the first unit, and it will cover approximation and error. When we take measurements, we are usually reading some sort of scale. For example, the scale of a ruler might have millimeters marked on it. Or maybe when you step on some bathroom scales to weigh yourself, that's also got a scale of maybe the kilograms or the tenths of kilograms. But when we actually measure the length of an object, or if you measure your own body weight, it's probably going to fall between two of those divisions. Like, it's unlikely that you're going to weigh exactly 70 kilograms. You probably weigh just a little bit more or a little bit less, and the device, in this case the bathroom scales, has rounded off to the nearest subdivision. So when the true length of an object falls between two divisions, in order to be able to discuss it, we need to estimate that measurement. Estimate the reading. And if it's on a ruler, we'll probably estimate to the nearest millimeter. Realistically then, the ruler is actually accurate only to the nearest half a millimeter. So if you see that you've got a length somewhere between 3 and 4 millimeters, well, maybe you could say, okay, that's 3.5 millimeters, but how could you confidently say that it's 3.276 millimeters? So really we can only estimate to the nearest half a millimeter. Or in general, a measurement is only accurate to plus or minus a half of the smallest division on the scale. So with a ruler with millimeters, it's accurate to plus or minus 1/2 a millimeter. Our set of scales that's marked in kilograms is going to be accurate then to plus or minus half of a kilogram. And a clock that has a seconds hand is going to be accurate to plus or minus 1/2 a second. Alright, let's move on then to the next example, where we've got a guy called Rod, and he uses a tape measure with graduations in centimeters. That means that on his tape measure we can only see centimeter markings, no millimeters, only centimeters. Now Rod measures his height, and he estimates his height to be 188 centimeters. Now we know that this estimation of his measurement is only accurate to plus or minus 1/2 a centimeter. So what is his height range? Well, the smallest possible height he could have, if we can only be off by as much as half a centimeter, would be 187.5 centimeters. And it might be as much as 188.5 centimeters if he kind of underestimated his true height by rounding down to 188. Next example, a rectangular block of wood. We measure it to be 78 by 24 centimeters. Now, of course, we might have rounded off. What are the boundary limits of the perimeter? So just as a reminder, we know that the perimeter is going to be the sum of all of these four sides. So if we've got, in the case of a rectangle, length and length and width, our perimeter is going to equal 2 of the length plus 2 of the width. Let's start by looking at the smallest possible perimeter we could have, just like we began by looking at Rod's smallest possible height. Now let's look for the smallest perimeter. Well, the smallest perimeter is going to occur when we've got the smallest possible dimensions. So what's the smallest? That's 78 centimeters. What's the smallest true measurement if we were able to measure it perfectly? It might have been as small as 77.5 centimeters. So let's suppose that that's the length. Our perimeter says we've got 2 of these. I'm going to call this then the perimeter small. And we have to add to it 2 of the widths. And the smallest possible width we could have would be, well, half less than that, 23.5 centimeters. And this must mean then that we've got 202, if I remember right. Yeah, I think this comes out to 202 centimeters. Now let's have a look at the largest possible perimeter we could have. And so now our length might be as much as 78.5, and maybe our width is as much as 24.5, and that gives us 206 centimeters. And so our perimeter is going to be somewhere in between 202 and 206 centimeters. And so this is what we would call the boundary limits. Okay, anything in between 202 and 206. So boundary limits and range, really the same term. We're looking for the smallest possible value and the largest possible value. Next example involves volume of a cylinder. And you might not remember that formula, so I've given it to you here. We've got a radius of 5 and a height of 15. So what are the boundary values? Well, let's start with the smallest possible volume that we could have, which would be pi times, well, our radius, smallest possible radius is 1/2 less, so 4.5 centimeters squared, times the height. The smallest possible height is 14.5 centimeters. And so let's actually work this out. You do have a pi on your calculator. Instead of typing in 3.14, which is not an accurate measurement, we can say second, and then this one here, the hat, and that will bring up a pi symbol, which is the exact value of pi, or as close as your calculator is able to express the exact value of pi. So we've got pi times 4.5, and if you want to do a square thing, we'll use this button right there, squared, times 14.5. And so the smallest possible volume is 922. So let's round it to 3 significant figures, 922. And the 4 that comes after that third significant figure, that's less than 5, and so we won't change the 2 to a 3. It stays at a 2, and everything afterwards becomes zeros. So 922, and because it's volume, centimeters cubed. The largest possible volume that we could have is going to be pi times, all right, what's the biggest possible radius? 5.5. Always plus or minus 1/2. And the biggest possible height is 15.5. Let's put that into the calculator. Second, there's my pi, times, 5.5 squared, times 15.5. And the largest possible volume, if I round it to 3 significant figures, would be 147. There's the third significant figure. The 3 afterwards is less than a 5, and so we're just going to keep the 7 as a 7, and everything afterwards becomes zeros. So I've got 1,470 centimeters cubed if I'm rounding to 3 significant figures. And so your boundary values then are 922 centimeters cubed to 1,470 centimeters cubed. Somewhere in between those two values your volume will be. And you'll notice that we get progressively less accurate as we go to higher dimensions. When we were only dealing with length or perimeter, we're able to get fairly close to the actual measurement. Now, that's a pretty small range. But when we're doing volume and we're multiplying multiple inaccurate dimensions together, we end up with a fairly large range. Okay, down here, an approximation is a value given to a number which is close to but not equal to its true value. So basically it's like rounding. This big number here, we could approximate it as 36.4. So that's an approximation, is where we're simply rounding a value to something else. On the other hand, an estimation will be an approximation which has been found by judgment instead of carrying out a more accurate determination. Like when we're measuring something. You know, we might see that the length of something falls in between 7 and 8 on a ruler. And so we will use our judgment in estimating what its true length is. So that's different from rounding. Rounding is when you've been given a very precise amount and you are simply rounding it. You're approximating it to the nearest, the nearest whole number or to 2 decimal places. Approximation is rounding. An estimation is an approximation which isn't found by rounding directly without kind of thinking about it like a computer might do it. You're actually invoking some of your own personal judgment in terms of coming up with this number. So for example, let's suppose we're trying to do the product of 38.7 times 5.1. We could estimate these values using our judgment. 38.7, well, that's pretty close to 40. And 5.1, well, that's pretty close to 5. This is much too difficult for me to do in my head. But 40 times 5 is very easy to do in my head. And so I've deliberately, using my judgment, I have rounded these values to 2 close numbers that are easy for me to multiply. Now the true value, if I multiplied these 2 things, would be 197.37. And so a good approximation using this true value would be simply rounding it to the nearest whole number of 197. So with the estimate, I used my judgment to be able to come up with a number. Approximation is rounding the true value in order to come up with a number. Now the error in rounding is found by taking the difference between the estimated value and the true value. So we always do estimated value minus the true value. Okay, the real one comes second. This is the inaccurate one. Now the IB formula booklet actually gives this a little bit differently. It gives it as VA, meaning the approximated value, minus VE, which is the exact value. So it's the same concept. The true value, the exact value comes second. The estimated or approximate value comes first. So in this example, let's find the error if a retail sales figure of, okay, what's this? Is this the exact amount or the rounded amount? This is the exact amount. And this one is your approximated amount. So we know the error is just going to be the difference between them. VA, 460,000, minus VE, 458, 110. Let's work that out on the calculator. 460,000 minus 458, 110. And we can see that our error is equal to 1,890, and I guess I need units in here, dollars. Now if we want to sort of get an idea about whether is this a big error, is it a small error, it's hard to say. If I'm dealing with billions and billions of dollars, this is a very small error. But if I'm dealing with only, say, $2,000, to be off by this much would be catastrophic. So in order to kind of get an idea about how big our error is, we need to do something called the percentage error. And we find this by comparing the error with the actual value and then expressing it as a percentage. And here's a little formula for you. The percentage error is the error, this thing up here, divided by the actual value, the real true value, times 100%. Now the IB formula booklet gives us a little bit differently. As before, it expresses the error as VA minus VE, approximate value minus estimated value, divided by the exact value. That's the actual exact or actual value on the bottom. And we multiply by 100% at the end in order to convert it into a percentage. Now we often find the absolute percentage error so that we don't have to worry about our error being negative. It's just going to be sort of 6% off. We're 6% off. Maybe we were 6% too high. Maybe we're 6% too low. And so by putting an absolute value sign around my error, it forces it to be a positive value.